All right, it's finally Friday. I know we're all excited about the weekend. Just to remind you, you've got a few things due today. Web assigned that you've been working on most of the week. Many of you probably have already finished it. 3 FRQs due today. And then today we're going to talk about one more step in differentiation. So if you haven't already downloaded 13, implicit differentiation is the title of it. One of the things that I hope you're getting used to is you can't forget anything. I've seen the product rule. You don't use the product rule some of the time. You don't use the chain rule some of the time. What you're finding now as you work through problems is you're having to use multiple things. You're having to use the power rule and some trig and a product rule and the chain rule. That's going to continue to build over the course of the year, so just expect that to continue happening. Easy derivatives are probably moving away from being something that you have to deal with. Today we're going to talk about another technique for differentiating. And before we do that, let's just take a little bit to review. When we talk about differentiation or finding the derivative, what does that mean graphically? How do we represent the derivative on a graph? It's the what on a graph? It's the slope. Yes, that's right. It's the slope. Not looking for anything real high-tech there. It's the slope of the graph at that time. Now, what does the slope, the derivative and the slope, they represent the rate of change of something. So they represent how fast something is changing. So the steeper the slope, the faster something is changing. The lower the slope, the slower something is changing. Well, I want you to look at this graph that we've got here. First of all, is this graph a function? No. No. Why not?
Because there's more than one y for that.
That's right. It's not a one-to-one correspondence. Some of you remember the vertical line test probably. If I draw a vertical line, it cuts it in two places, so it's not a function. However, should we be able to find the slope at any given point? Should there be a derivative at any point on this graph? Intuitively, it says yes. I mean, I can find a point. This graph is changing, so there should be a derivative. There should be a rate of change associated with it at every point. So we should be able to find a derivative for this graph. The way to do this is something called implicit differentiation. Okay? Now, we're going to use the same rules that we've been using, just now we're going to differentiate implicitly. What we've been doing is explicit differentiation, where we could solve it for y and then get an answer out that way. This, if we solve this for y, some things we could solve for y, like this one we could, but we wind up with a much more complicated solution to it. So when we derive something implicitly, this is the process we go through. We still use the same rules that we've had before. So if this is my expression, to differentiate this, the derivative of something squared is what? 2 times that something. So the derivative of y squared is going to be 2y, but then we multiply it by the derivative of y. Well, we don't know what the derivative of y is. That's what we're trying to find. But what could we put in place of that? We can put dy over dx. Now, that's just one name that we use for writing the derivative of something. We use y prime sometimes, different names, but that's the best name for you to use in this. And as we go through, I'll explain a little bit more, maybe give you a little bit of a hint as to why I think that's beneficial. So when we're taking the derivative of y squared, it's 2 times y times dy dx plus, what's the derivative of 2x? 2. Okay. Now you say, well, why do I have to take the derivative of x? you actually are taking the derivative of x. What is the derivative of x with respect to x? What's dx over dx? 1. Isn't anything divided by itself 1? So we haven't been writing this down, but we've actually been doing that. It's the derivative with respect to x, dx over dx, so there's no reason to write it. So we simply say 2 equals, what's the derivative of 8? 0. So suddenly we have an expression. Now, how can you find out dy dx here? What do you need to do to solve this for dy dx? What do you need to do to get dy dx by itself? It's just straight old algebra now, okay? So we're going to subtract 2 from both sides. We have 2y dy over dx equals negative 2. Now, what do you think we ought to do? If we're solving for dy over dx, what do you think we should do at this point in time to get dy dx by itself? By 2y. We divide both sides by 2y. So we find out that dy over dx is negative 1 divided by y, because the 2's will cancel. So that's the derivative of this particular point, of this particular function here. All right? Does that seem to be right? Well, let's see. When right here at, if we were just guessing here, right here about this point, that looks like 2. What does the derivative, that looks like the point 0, 2. So what should the derivative at that point be? Negative 1 over y, which is what? Negative 1 over 2. Does that look like the derivative is negative 1 over 2? It doesn't to me. So did we do something wrong? Maybe I've got the wrong. I don't think this graph goes with this. I don't think this equation goes with this graph. Okay? So let's just back up for 30 seconds and forget I even tried that. The algebra that we did here is correct. This is the right process for finding the derivative. But now, this is an algebra 1. So I'm not going to give you a section on the test that says use implicit differentiation. You've got to be able to recognize when do you use implicit differentiation, when do you not use implicit differentiation. When you look at this equation, you use implicit differentiation. What clues you looking at this equation that you use it? We've got y squared in there. We've got something happening to y that's difficult to undo. So we're squaring y, we're taking the square root of y, we're finding a trig function of y, we're finding it's e to the y, it's a logarithm of y, something like that. So when you take the derivative of this, tell me what you're going to get for the derivative of x squared. Anyone? What? 2x. 2x. What are you going to get for the derivative of y squared? 2y dy dx. Okay? You can write it as dy dx or y prime. I'm going to write it as y prime this time. Doesn't matter, okay? It's both meaning the same thing. Equals what? 0. So if we're going to solve this for dy dx, solve it for y prime, tell me what we're going to wind up with. Negative x over y. So that's what that expression looks, that's what the derivative of that looks like. Does anyone know what the graph of x squared plus y squared equals 81 looks like? X squared plus y squared equals 81. X squared plus y squared equals 81 is a circle. It's a circle. The radius on this is 9. So now, does this make sense? If we were talking about the slope at this point, this is the point, what, over 0 up 9. The slope looks like it should be 0. If we put 0 over 9, we get 0 out of that. What do you think the slope should be right here? Just looking at it graphically, what do you think it should be? Undefined. So if we put 9 over 0, we get undefined. If we come over here somewhere, that's going to be a positive x number and a positive y number, but the slope is negative. We're going to get a negative number. So that's just giving you a little bit of a graphic representation of this, that it does work there, okay? So we can find the derivative of any equation now with x's and y's in it. What's the derivative? Let's look at these two and see if we can confuse ourselves. How are these two different? Just by looking at them, how are they different? One has y, one has x. Notice that both of them say d over dx. What does that mean? The derivative with respect to x. That means x is what we're measuring everything against. So everything, the derivatives we've been taking have all been derivatives of x, dy dx. So this derivative is going to be what? Can anyone tell me? 3x squared. Yes, that's what we've been doing. How is it going to be different over here trying to find the derivative of y cubed? What are we going to get? 3y squared. Oops. 3y squared, but we got something else. Because this variable is not the same as this one down here. What we're taking, the derivative of it is not the same, so it's going to be times y prime, or dy dx, whichever way you want to write it. Okay? Is that making some sense to you? That's just the process that you've got to go through. So when we look at something like this, we've got x squared and y cubed in there. There's no sign between them, so we're multiplying them. So what does that tell you about taking the derivative? Since they're being multiplied, what do you have to use? Product rule. Okay? So if we're taking this, we've got to find the first and second. What's the first thing in here? What would you call the first thing? X squared. This is my first. Y cubed is my second. So we're going through first, x squared, times the derivative of y cubed. What's the derivative of y cubed? 3y squared, almost. Y prime. Got to remember the y prime. That's what students are going to forget. That's where you've got to be careful of. First times derivative of second plus second, y cubed, times derivative of x squared is what? 2x. Why don't I have to put x prime there? Right. You're taking the derivative with respect. Think of it this way. Derivative is rate of change, right? This is saying the rate of change of y with respect to x. So how fast is y changing as x changes? That number wouldn't be 1 necessarily. You follow me? But how fast is x changing with respect to x? If x is changing and x is changing, they're changing at the same place, at the same rate. If y is changing and x is changing, they could be changing at different speeds. Anytime it's a variable other than this bottom one down here, which for right now has always been x, it won't always be, but right now it's always x, you have to put the derivative of that other variable in there. You have to put y prime in there. Is this clear as mud? Good. Let's see if we've got. So determine the slope of the tangent lines to the graph of the following circle when x equals 1. Okay? Determine the slopes of the tangent lines to the graph of the following circle when x equals 1. What's the first thing you need to do here? I'll work on it there for a second, then we'll come back and talk. Has anyone got a derivative that they want to share with us? The formula for the derivative? Any brave soul out there? Jasmine's brave. Come on. Negative x divided by y. Anybody else get that? Very good. Isn't that the same thing we got a while ago when it was equals 81?
Yes.
Does that make sense? Why?
Because you only get whenever you have x squared and y squared, it's just going to be.
Yeah, because this 9 over here is going to go to 0 no matter what that number is. So negative x over y. So great, there's our formula. Now that doesn't answer the question. To determine the slope of the tangent lines. Slope of the tangent lines. That implies there's more than one line, is there? Okay, where are the lines? How can that be? When the circle x equals 1, well, we've got 2 points, don't we? We've got x being 1 up here, and we've got x being 1 down here. So how are we going to find the slopes of these two lines? Any suggestions? How are we going to find the slopes of these two lines?
Plug in one for x.
Very good. We've got to get, we've been doing this for several weeks now, so we know we're going to put 1 into the derivative. What's the problem with just putting 1 into the derivative this time, though? We need the y. So how do we get the y? Jasmine's exactly right. 1 plus y squared equals 9. So y squared equals 8. So y equals plus or minus the square root of 8. Now, this poses a problem, or this gives us an opportunity to talk about something that confuses students sometimes. Notice that I wrote plus and minus 8 there, and that is the correct answer. But now, in one of your homework problems, I don't remember which one it was, you wound up with something like this for an answer somewhere in there, and you had to put 25 in there, and the answer is just 3/5. Why isn't it plus or minus 5 right here? And plus and minus 3/5. Why is this right to just be one number, but over here it has to be both of them? 2 tangent lines, yes, but I mean, if we didn't have the picture, it'd still be right for it to be 2 there. And whether we've got a picture or not, it's still right for there just to be one answer here. How do we know, and this is a bigger question than calculus right now, how do you know when you look at this problem that there's only going to be one answer, but when you look at this problem, there's going to be 2 answers?
Is it the degree?
That's a part of it, yes. Right here, the fact that we've got y squared tells us there has to be 2 answers. So there has to be 2 answers here. We are introducing a square root here, okay? And that's the word I like to use. There was not a square root written in this problem to begin with. We're placing a square root in there. Anytime we introduce a square root, there's going to be 2 answers. How does that differ from this problem here? Here, there was already a square root in the problem. We didn't throw it in there to help solve it. If the square root is written there, it's understood to be positive unless I put a minus sign in front of it. Does that make sense? That coincides with everything else. When you look at that 3 up there, you don't say, I wonder if that's a positive 3 or a negative 3, do you? It's understood to be positive because there's not a sign written in front of it. Here, it's understood to be positive because there's not a sign written in front of it. Okay, so we've got y equals plus and minus 8 out of there. Okay, so now we're going to put in one of the slopes then is going to be negative 1 over the square root of 8. And the other slope is going to be negative 1 over the square root of negative 8. Or 1 over the square root of 8, right? So those are our two slopes. Which slope goes with which point? If we label this point up here A and this point down here B, which one of the slopes goes with A? How do you know that? Exactly. Couple ways you can look at it. We put a positive square root of 8 in there. That's up. That goes up there. That slope is negative also, right? That number is negative, so those have to go together. These have to go together. Could you write the equation of the tangent lines now? You've got your x's, you've got your y's, you've got your slope. You could just write them down there, okay? So every problem that we've already done, we could do all of them with just so many more things now because we can do implicit differentiation. Okay? Implicit differentiation can get very lengthy. You're going to have some challenges with some of the homework that you're going to have there, okay? Because they get lengthy. But it allows us to find the derivatives of any general expression that has x's and y's in it now, okay? Any questions? All right. Yes, sir.
The square root of 8, isn't it the same thing as 2 times the square root of 2?
Yes, you could write this as 2 root 2 if you wanted to, yes. Yeah, you'll get the same thing there, okay? All the way through algebra, we have taught you that you have to rationalize everything. And actually, if you wrote negative 1 over 2 root 2 down for Miss Dillard for an answer, she probably marked it wrong because you have to can't have any square roots in the denominator. Those rules go out the door with calculus, okay? Negative 1 over root 8 is an acceptable answer. Negative 1 over 2 root 2 is an acceptable answer there, okay? You don't have to rationalize any longer. Okay, you've got WebAssign, FRQs, and now homework 13 that you can work on. Next week, we're going to work on 2 things, logarithms and exponentials, and then we'll be ready for our next test, hopefully early the following week there. Ask questions as they arise here.